Okay, welcome all. Welcome to this third webinar of the WCRP Digital Earth's Lighthouse Activity webinar series. My name is Huw Lewis from the Met Office in the UK, and I'm one of the co-conveners of this series, along with Kelly Nunez from NCAR, who unfortunately had a last-minute emergency, so can't join us today. This webinar is part of an ongoing bi-monthly series organised by the WCRP Digital Earth's Lighthouse activity. And the aim is really to maintain more regular and open dialogue between active researchers and users on the development and evaluation of kilometre-scale global and large domain models working on kilometre-scale modelling around the world. And you can find via the web link that's advertised on this slide the series that we have planned going through 2024, and also the recordings from the first two events that we held back in November and September of last year. The focus for today is on multi-year climate simulations. Just before I introduce our speaker for today, a few items of housekeeping and logistics. So during the talk, please feel free to pose questions. You'll find at the bottom of the Zoom screen a Q&A feature, and please leave questions for the speaker via that panel. You can also upvote the questions there that are being posted by others with the thumbs up icon to highlight which questions you'd like for us to get to in the Q&A before other questions. So have a look at what's coming in and vote away. There's also a chat function. We'd ask that you reserve that just for sort of technical issues that might come up through the session. I really hope we'll have a lot of engagement and interaction through the Q&A later on in this session. And if a bit like me, you tend to not ask questions in these kind of events, maybe the challenge for you today is to offer a question, and I'm sure it will be of interest to the rest of us on this call. So please don't be afraid to post your questions in the Q&A. Okay, with that, it's my absolute pleasure to introduce today's speaker, Dr. Daisuke Takasuka. He is a project assistant professor at the University of Tokyo. Daisuke obtained his PhD in March 2020, and his current research interest is on the cross-scale interaction of tropical moist and dry processes, and on global cloud resolving weather and climate modelling, as he'll describe to us in a second. And Dr. Takasuka is a member of the WMO WGNI MJO task force. So a big thank you to Daisuke for volunteering to present your work and to share your experiences with us today. And with that, we therefore warmly welcome you and look forward to your presentation on multi-year climate simulations with kilometre scale NICAM, strategies, successes and outlooks. And with that, Daisuke, thank you, and the floor is yours.
Yeah, thank you for the introduction. Okay, maybe you can see the slides.
Yeah.
Okay,
And
so good morning. Yes. So good morning, good afternoon, and good evening. I'm Daisuke Takasuka from the University of Tokyo. And first of all, thank you so much for giving me an opportunity to talk about the NICAM activities. So in this talk, I'd like to talk about the activity of the K-scale climate simulation using a NICAM. So yeah, this activity is one of approaches proposed in a Japanese research project named as the DNA Climate Project. This details has already been published as Amira et al. In 2024 in BAMS. So if you have interest, please read it. And this work is also supported by many collaborators. Okay, so the NICAM has been used as a global convection resolving model, which treats the deep convection and the bulk cloud processes explicitly without any cumulus parameterizations. So in this framework, the dynamics are directly coupled to cloud-related local thermodynamics. And that is the moisture and the heat is supplied by surface proxies related to in situ winds computed by the explicit fluid dynamics. And in response to more buoyant column, the local circulation is established around it, and the heat and moisture is almost locally redistributed within a column. So we can consider that a cloud is a fast response without disturbing slow-scale circulations unnecessarily. So related to this merit, GCRMs can represent the heat and moisture transport more accurately and the spontaneous realization of the hierarchical structure of cloud systems, as shown in these comparisons. That's why the NICAM has been intentionally used as a GCRM framework without any Kermas parameterization. So in the history of the NICAM activities, we have already shown that the GCRMs can work well, at least for the S2S scale simulations. So an example of this is the first success in the hindcast of the MJO simulation. So looking at these two time longitude diagrams of equatorial precipitations, you can see the NICAM can succeed in reproducing the slow eastward migration of large scale precipitation systems. So considering that the MJO consists of many convective systems and is also related to the moisture fields, we can say that this success is a result of solving a local response to heat and moisture accurately. Meanwhile, this treatment of GCRMs is a kind of weather-focused framework. So, for example, Amira et al. Discusses potential limitation of this framework to S2S scale phenomena, such as the tropical cyclones and MJO. So, in other words, they wonder if GCRMs can keep their good performance even for longer time scales that are in which the climatological energetics and their fluctuations are more important. So in their argument, it is compared with a conventional GCM framework. So conventional GCMs do not need any details of microstates such as individual cumulus activity, but instead of it, the kind of quasi-equilibrium assumption at grid scale partly helps the energy balance, despite degrading the simulations of faster scale variations possibly. So this is just like the analogy of the equilibrium statistical mechanics and thermodynamics, in which we don't need any details of molecular motions to obtain the macroscopic variables, and the microstates follow some ensembles characterized by the macrostates. So in this context, we may say that the GCRM long-term simulation are as if the macrostates were obtained by the direct computation of molecular motions. However, in this treatment, the exact computation of microstates is needed, which has not been achieved yet in the current GCRM framework. Now, also, the microstates or clouds have no information or assumptions for the macrostates. So that's why accumulating local responses or clouds in GCRMs do not guarantee obtaining the accurate, slowly varying equilibrium states because of mesoscale uncertainties. So specifically, behind this issue is obvious fact that the K-scale GCRM still do not resolve all of turbulent motions and cloud characteristics. So such turbulent mixing and microphysics within a column can be critical to altering the timescale of explicit mesoscale circulation in GCRMs. So for example, this is because of the direct coupling between the dynamics and the column physics in the GCRMs. So for example, our difference of the turbulent mixing contributions is a source of the difference in the cloud organizations, at least in NICAM. So looking at these figures, for strong turbulent transport cases, very efficient turbulent transport of heat and moisture and tends to stabilize the column even without explicit circulations. So individual convection can be inhibited, leading to excessively large-scale cloud organization systems. So yeah, based on this kind of large sensitivity to the cloud organization characteristics, which is certainly important to the climate formations, we have to take a careful look at impacts of microphysics at a turbulent mixing on deep convections before entering the K-scale worlds. So based on these introductions, I'm now talking about the specific strategies and the results of the NICAM improvement toward the reliable K-scale climate simulations. Okay, so as mentioned earlier, it is not straightforward to do realistic simulations with GCRMs. So reflecting these situations, we actually have two representative settings in the NICAM, depending on what timescales we are specifically interested in. So one is the high-resolution configurations, which prioritizes the better radiation distributions in climate simulations. In fact, the high-resolution configurations can succeed in reducing the OLR biases globally, which supports the good radiation balances at the TOA. Meanwhile, this configuration fails the spontaneous realization of the MJO. So that's why we have the other configurations, named as the MJO configurations, which prioritizes the realistic MJO representation in S2S scale simulations. So the fact that we had to have two different configurations imply that model physics in GCRMs may not have degrees of freedom to satisfy the requirements for better weather and climate simulations. So in this activity, we try to find appropriate timescale of explicit local circulations and add degrees of freedom in model physics. Okay, so as a first step of this strategy, in order to grasp the convection characteristics briefly, we first examined the OLR snapshots simulated by the high-resolution at MJO configurations at a 3.5 kilometer NICAM simulations following the diameter winter protocol. So this is a courtesy of the Dr. Tamaki Suematsu at the RICAM. So the differences in between the two configurations lies in the cloud microphysics treatment, of which the details would be explained later. So anyway, we can see that the high-resolution configurations can generate the more TC-like structure. And the MJO convector envelope here seems to be split into two vortices. Whereas the MJO NICAM configurations can generate more organized cloud systems associated with MJO here. So yeah, these contrasts follow our expectation that the cloud microphysics can alter the deep convection characteristics. And we also expect that these diversities can result from the difference in moisture remaining at consumption timescale and processes in each other. So for these two configurations, I conducted the process-oriented diagnosis for moisture convection relationships. First, we're picking up the convection core using the 700 hectopascal vertical wind velocity as indicated by green circles, and then we examine the later log composite evolution of moisture at the detected points. So this figure, the x-axis in this figure is a time, and the log 0 corresponds to the timing of the convective core detections, and the y-axis is pressure height. So you can see that the gradual shallow to deep moisture transitions in the high-resolution configurations, and our interest is how different is this from that in the MJO configurations. So the answer for this question is provided in color shading in this figure. And you can see the two clear differences. So one is that more moisture tends to be accumulated, and vice versa in the free troposphere before deep convection triggering. This implies that less prone for individual convection to trigger. The other is more moisture is detrained in the mid-troposphere in accordance with the convective development. So yeah, these results suggest that microphysics can impact convection triggering and detrainment, and which in turn moderate the large-scale circulations. So schematically summarized here, for the MJO NICAM calculations, the individual convection is hard to be triggered, and moisture tends to be detrained in accordance with the convection development. So under these microscopic characteristics, for convection to be in balance with the large-scale substance due to radical cooling, or more large-scale organized cloud system can be preferred by a moisture convection radiation feedback. So yeah, this characteristic is advantageous to better representation of the MJO. But this configuration also has some side effects on the mean radiation and circulation fields, as indicated by the significant reduction of OLR at the TOA and the two active convections over the maritime continent. On the other hand, for the high-res NICAM configurations, individual convection is easily triggered, and the moisture is relatively fast overturned. So local convection can be sufficiently balanced by large-scale substance, which means that the large-scale organized system such as the MJO is not preferred in exchange of the better representation of the mean radiation balances at the TOA. So looking at these two results, it would be reasonable to take an intermediate feature between the two configurations. So we decided to improve the model by retuning of microphysics and a new treatment of turbulent mixing and increase the vertical resolutions while taking care of the moisture convection relationships diagnosis. Okay, so first, I'd like to introduce the microphysics retuning. So here we take care of the vertical profiles of water substances because they can regulate heating and the temperature profile that are important to the convection development. So comparing their tropical mean profile between the high-res MIP and MJO configurations, we can see some significant differences. For example, in the MJO configurations, there are much less cloud ice, much more grow-pale, and more snow at the higher altitudes, partly because of adopting the older version of microphysics scheme in the MJO configurations. And actually, some of these features are unrealistic. So this problem can be resolved in the high-res MIP configurations by the scheme updating. But anyway, at the MJO configurations, we can expect the more melting near the freezing level. More importantly, at MJO configurations, the fall speeds of rain and snow are intentionally reduced to enhance rain evaporation and snow productions. So these changes lead to more evaporated cooling in PBL and more radiative heating in the mid to upper troposphere, which can affect the static stability. So in fact, looking at the stability differences between the MJO and the high-res MIP configurations, the MJO configurations has more stable layer in PBL near melting level and below the top of snow clouds. So these result stability profiles are consistent with less convection triggering and more moisture detrainment in the mid to upper troposphere for the MJO configurations. So based on this insight, in order to obtain the intermediate characteristics between the high-res MIP and MJO configurations, we retune the fall speeds to their intermediate values between the two. So these retunings give us our expected static stability changes as shown in this vertical profile of the stability difference from the high-resolution configurations. So the revised configurations has more stable layer in PBL compared to the high-resolution configurations, but its amplitude is reasonably reduced compared to the MGL configurations. And we also find a more stable layer in the mid to upper troposphere because of radiative heating associated with more snow productions. So yeah, consistent following this static stability changes, the moisture evolution associated with deep convection is similar to that in the MGL configurations as shown in these figures. In terms of more moisture accumulations before convection triggering in PBL and more mid-level moistening after deep convection triggering, but its amplitude is also reasonably reduced. So yeah, these results are desirable features in this tuning. And we also introduced cloud ice falling to consider more plausible cloud physical processes. And this treatment also helps us obtain the better radiation balances at the TOA. Okay, so another important improvement is the implementation of additional turbulent mixing effects. This is motivated by the fact that the turbulent mixing effects cannot be completely separated from those at a subgrid scale in CRM scale. So we implement the Leonard term indicated by these equations. So this color shading in this figure show the vertical moisture fluxes computed by the Leonard term, and the contours show the upward wind velocities. So you can see the active moisture transport near the convective cores by the Leonard term, which means that the Leonard term can supplement the lateral moisture mixing associated with deep convection. So consistent with this behavior, looking at the moisture evolution associated with deep convection, we can see the moist anomalies in accordance with the convective development, and we can also find more moisture detriment in the mid-troposphere. So this suggests that a mid-level moistening is naturally represented without disturbing convection triggering thanks to the implementation of the Leonard term. Okay, so actually we confirmed this improved NICAM has succeeded in the reducing long-standing biases in terms of both mean characteristics and weather disturbances. For example, these two figures compare the time, latitude diagrams of monthly mean precipitation over the Central Pacific. And the contours indicate the trim observations. So yeah, for the high-resolution configurations, there is significant double ITC biases, especially for boreal fault, but this biases is largely mitigated in the revised configurations. And we can also simulate the seasonal march more realistically. And we also check the performance of the spontaneous realization of the MJO by looking at the Hoffman diagrams of low levels on the wind fields in high resolution and revised configurations. And we can see that the revised configurations can reasonably reproduce the MJO with the intra-seasonal quasi-periodicity compared to the high resolution configurations. And we also mentioned the significant impacts of the vertical resolution enhancement on the mean radiation fields. So these two figures compare the mean OLL biases between the 38 vertical layer and the 78 vertical layer simulations. So the 38 vertical layer simulations has a significant negative OLL biases. Negative means that downward radiative fluxes of the TOA. But this large biases is drastically mitigated in the 78 vertical layer simulations. This is because of the better representation of the cirrus clouds associated with the increased particle resolution near the turbopoles. And increased particle resolution also improves the representation of the mid-latitude westerly jet positions. So these two figures compare the mean, zonal mean, zonal wind biases, and we can find that the 78-layer simulations can significantly reduce the biases in the positions of the westerly jet and their amplitude. Okay, so yeah, these model improvements are based on many 1-year sensitivity simulations at a 14-kilometer mesh. But this workflow is not necessarily easier because of in terms of the data handling. So yeah, because the NICAM output data on icosahedral grids, we need to convert the icosahedral data to the latitude longitude grids in order to analyze the data more easily. So the bottleneck of this post-process was resolved by Dr. Chihiro Kodama at the JAMSTEC. So specifically, he adopted the algorithms of the file separation and the MPI gather technique in converting the icosahedral data to latitude longitude diagram, latitude longitude grid data. So specifically, it first reads the regional icosahedral data in parallel, and after that, we collect the icosahedral data in every rank and remap and write latitude longitude data simultaneously in parallel. So thanks to this improvement of the post-processing, we can succeed in the 7 to 9 times speeding up in post-processing, which is advantageous to do many high-resolution sensitivity experiments very efficiently. And this algorithm has also good weak and strong scaling. So even if we change the horizontal resolution, this good performance can be maintained. Okay, so we are now introducing the present status of MIP-type climate simulation by K-scale NICAM as another success. Okay, so using an updated model configurations, we are now doing the 10-year MIP-type simulations at 3.5 kilometer and 78 particle resolutions. So these simulations is from January 2011, and external forcing is obtained from the Harris-Smith protocol, and the SSD and ice fields are predicted by a slab ocean model with a nudging to the austere product. The microphysics turbulence, radiation, and the gravity wave drag forcing is as follows. So this simulation provides such beautiful movies, actually, in terms of the very beautiful convective evolutions and a very detailed convective clustering. But we are interested in how is that performance. So I'm now picking up some of notable results from our K-scale climate simulations, in which the 8-year integration has already been finished. And so we start with describing the precipitation statistics. So these two figures compare the mean precipitation distributions between the ZPCP and the NICAM simulating data. So first, looking at the tropical precipitations, the simulated precipitation fields have no WITCC and a realistic zonal contrast from the Indian Ocean to the ITCC regions. So this is a drastic progress compared to the high-resolution NICAM configuration, high-resolution NICAM simulations at 14-kilometer horizontal resolutions. And we also succeed in reproducing the realistic extratropical precipitation in terms of the storm track position. And this figure is the PDF of the daily mean precipitation, and this figure suggests that the K-scale NICAM can succeed in the reproducing the observational precipitation PDF compared to 14 kilometer mesh. So this suggests that the more quantitative evaluation for extreme precipitation becomes possible in our simulation. Okay, next we examine the statistical characteristics of the MJO and the associated cross-scale interactions. So for a comparison with a conventional GCRM, we also plot MIROC6 simulation. So these three figures compare the MJO composite Hochmiller diagrams of OLR at a westward propagating synoptic scale, OLR variance anomalies. So, for example, for the observations, we can see the smooth eastward propagation in the detection of 20 MJO events. And we also find enhanced activity within the MJO convective envelopes, especially over the Indian Ocean. So these observation points can also be obtained in the NICAM simulations, specifically the number of MJO events and the smooth propagations and the relationship between the MJO and the synoptic scale disturbances can be captured very well. Yeah, MIROC6 also captures the MJO to some extent, consistent with the good MJO models in CMIP6 intercomparison, but we can say that more realistic initiation frequency, propagation, and hierarchical structure of the MJO can be simulated in the K-scale NICAM compared to conventional GCRM. And better, more realistic representation of tropical cyclone intensity is also a clear merit of our K-scale NICAM simulations. So this plot shows the relationship between the maximum 2-meter wind speed and the SOP relationship for detected TCs. And the reddish and the blue colors correspond to the 14 and the 3.5 kilometer simulations. So in the 14 kilometer simulations, we have weak maximum wind speed biases, especially for intense TCs. But this biases is drastically mitigated at 3.5 kilometer simulations compared to the observational estimation from the Atkins and Holiday in 1977. So related to this improvement, K-scale NICAM can also reproduce super typhoons with surface wind speed of more than 64 meters per second. Very well. So this realistic simulation of intense TCs is associated with the fact that the K-scale NICAM can represent the rapid intensification appropriately. So this map shows the tracks of category 5 TCs and the location at which the rapid intensification occurred. So we can find that the K-scale NICAM can reproduce the Cat 5 TCs and associated rapid intensification very frequently over the Western North Pacific. So looking at the right panel, which shows the observed trend of rapid intensifications, this region encounters a significant increased trend of the rapid intensification. So the better representation of super typhoons and the rapid intensification over this area is very advantageous to the argument about the future projection of very intense TCs. And also looking at the time series of surface wind speeds of the category 5 TCs with rapid intensifications, we can find that most of category 5 TCs have similar intensification rates after the weak intensification period. Okay, until now, I talked about the successes in our K-scale climate simulations, but it is also a fact that there remain big challenges in biases and error compensations. So as the last sections, we'd like to talk about them and also present the future planned simulations. Okay, the first issue is that NICAM has too few log clouds. So these two figures compare the 5-year mean OLR and OSR biases. And the cooler color indicate the downward radiative fluxes at a TOA. So the OLR fields is a relatively bias-free, and the global mean bias is almost zero. However, the mean OSR fields have significant negative biases, especially for the low cloud regions. So this means the overestimation of shortwave radiation incoming, especially in low cloud regions. So yeah, we've already specific reasons. One of specific reasons for this, which is overactive turbulent mixing due to no consideration of partial clouds in our turbulent schemes. But another is speculated to be still coarse particle resolutions. So to test these speculations, we conducted 50-day sensitivity experiments in which the particle layers in plant-boundary layer and the lower free troposphere is increased. So this figure shows the mean OSR differences between these two simulations. And this figure suggests that this figure focuses on the off-period regions. And it suggests that increased particle layers in PBL and the lower free troposphere help more shortwave reflection in the shallow CMS regions. Also, its impact on the stored CMS region is non-trivial. So anyway, more sophisticated diagnosis of turbulent mixing lengths is required in our Mera-Yamada-Nakanishi scheme. Okay, so the second point is about error compensations. So here we take microphysical aspects as a clear example. As mentioned in the implement of NICAM, we retuned the fall speeds of rain and snowdrops. So this was achieved by a change in constant C in the relations between the bulk terminal velocity and the diameters, which corresponds to tuning of target diameters of 4 droplets in the single moment scale. So for example, this figure compares the relationship between the observation and model configurations. And it shows that the Harris-Smith configuration fits this relationship near 1 millimeter diameter. So 1 millimeter is a typical value of raindrops from deep convection, but the revised configuration assumes smaller raindrops in falling processes, which result in the slow fall speeds of raindrops compared to the observation and the Harris-Smith configurations. So at this moment, this tuning is necessary to obtain the nice moisture convection relationship by enhanced evaporative cooling, but it can be a result of error compensation. A possible interpretation for this is the underestimation of dry intrusion, the social wells entrainment between the PBL and the lower free troposphere. So we have to take a look at turbulent transport processes more carefully. Okay, so the last point is about convective organizations. So this plot shows the relationship between the size of precipitation clusters and the total area with each precipitation size. The precipitation clusters are defined as the full connectivity detection on 1.25 degree in the tropics. And compared to the conventional GCRM result from MIROC 6, indicated by blue lines, NICAM follows the observed relationship overall. But looking at the small scale convective organizations, its frequency is still overestimated. So this biases has already been mitigated by the model improvements described so far, but we have to keep this realistic feature in this mind for the future model development. Okay, lastly, we'd like to introduce the future plant simulations. So first, we will start soon 10-year ocean-coupled simulation using a NICAM, which is the ocean-coupled version of NICAM, as 3.5 kilometer atmosphere and a 0.1 degree ocean. So we've already allocated computational resources on supercomputer Fugaku for these simulations. And in these simulations, we will adopt the same physics settings and period as those in the 10-year NB type simulations. And in the 3 years, we also plan the 30-year K-scale NICAM NICOCO simulations for the present climate situations. So yeah, towards success in this plan, model acceleration by the GPU coding is now intensively tested. So this plan is in anticipation with performing centenarian NICOCO simulations at this resolution data in 2030. And another topic is the intercomparison of year-long K-scale realistic simulations we are now planning, which is one branches of diameter 3 intercomparisons. So yeah, this intercomparison is targeted at the intensive analysis of the seasonal evolution of large-scale circulation simulated in the K-scale storm reciproc model. So if you are interested in this activity, please welcome joining us. Okay, so let me summarize my talk. And at this moment, a 3.5 kilometer mechanic climate simulation succeeds in the seamless and realistic representation of the climate simulus systems. But K-scale resolution does not resolve systematic model errors automatically. So be more aware of impacts of microphysics on unresolved turbulent mixing. We decided to, we aim at controlling how moisture is consumed and remained by convections. So by taking care of the moisture convection relationship, via microphysics retuning, implementation of additional turbulent mixing and increased particle resolutions, we succeed in the simulating precipitation statics and many weather phenomena. But we must mention that resolving too few low cloud and error compensation problem is our next big step in our activity. Okay, thank you for your attention. Let's stop my talk here.
Thank you so much, Daisuke. Hopefully you can hear me okay. I seem to be having problems turning my video back on, so you may have to put up with the voice from the ether. Trusting you can hear me okay, encouragement for all to add some questions into the Q&A. We have some time now to work through a few questions you may have. So please don't be shy in putting forward some questions, and we can work through those. We can kick off with a question from Aaron Donahue, who asks about you talked about the vertical resolution, but how high is your model top, and do you have considerations on that?
Yeah, thank you for the questions. The model top for 78 vertical layers is about 50 kilometers. So that's not cover fully the stratosphere. And we also adopted the sponge layer from above the 30 kilometers or 35 kilometers. So yeah, the model top is about 50 kilometers. Yes.
Thank you, Daisuke. And a question here from Ashish Mitra. It's fantastic to have you on the call, Ashish. In your MJO setup AMIP runs, how frequently were your observed SSTs updated?
Okay, yeah, thank you. Yeah, so MJO setup AMIP runs the updated interval is daily SST. So we use the daily SST to nudge the SST predicted by slope ocean model.
Can I ask on that theme what your expectations are on moving from the slab model, the slab ocean model, to the full 0.1 degree NICOCO system? Do you have insight on that already?
So you mean that
moving to a full ocean model?
Yeah. So we are planning fully ocean, the use of the fully ocean couple model simulations. And we will start the ocean-coupled simulations at the 0.1 degree ocean breeze and 3.5 kilometer atmosphere very soon. So yeah.
And can I ask, do you have an expectation on how your results might be impacted by that change?
Yeah, actually, the coupling with the ocean, coupling with oceans generally affects generally improves the MJO simulation or MJO simulation by the better representation of the relationship between the moist static energy and the ocean heat content. So that coupling has a better impact on the MJO simulation. And but I don't know how the coupling brings about the mean state, because of the NICAM has a few poor representation problem of low clouds, which contributes to unrealistic warming to SSD. So yeah, we will have to examine the impacts more carefully.
Let's just stay on the SST and the ocean theme with a follow-up from Ashish, who asks about with your use of daily SSTs rather than sub-daily, well, how do you resolve the diurnal cycle of air-sea interaction in your uncoupled runs, and maybe your considerations of how important that might be?
Yeah, actually, I haven't checked the details of the diurnal cycle of air-sea interaction in coupled runs, but we adopted the relaxation time of slab ocean model to seven-day time scales. We adopted a seven-day relaxation time of slab ocean model. So we expect that we can succeed in representing the sub-daily timescale temperature fluctuations associated with the shortwave radiation incoming and ocean cooling associated with the more surface heat fluxes. But we cannot answer the quantitative evaluation of this process. But anyway, slab ocean fields are the shortwave incoming and SS cooling due to surface fluxes. So we expect this process is somewhat reproduced within a sub-daily scale.
Perfect. There's a couple of questions here from Iko Voigt. We'll start with a question saying, is snow interaction with radiation in NICAM? And do you think it's an important part of your microphysics sensitivity?
Yeah, that's a very good point. Yeah, I think that interaction between the snow clouds and radiation is important because of the for example, the stratiform clouds is composed of many snow clouds, and which causes the anomalous radiative warming. And that anomalous radiative warming can feed back onto the upward motions due to the weak temperature gradient balances. So, which in turn affects the efficiency in the moisture transport in the mid to upper troposphere. And so that's why it is, I think the full interaction between the radiation processes and the cloud microphysics is very important to controlling the cloud organization characteristics in my cloud microphysics tuning.
Okay, thank you. And second question from Iko asking, have you looked at why the jet bias is so much reduced in your revised NICAM version?
Yeah, actually, I haven't checked the reason why quantitatively, but one of potential reasons for this is the better representation of gravity wave, better representation of momentum transport associated with gravity wave propagations. Yeah, the vertical resolution enhancement partly helps such kind of propagations of gravity waves. So that's one of possible reasons for this. But yeah, as you questioned, we need to check the momentum budget quantitatively.
And can I ask, when you were showing the direct comparisons between the 3.5 and the 14 kilometers, were they both using the updated physics configurations?
So in terms of the jet position, right?
Yeah, for example, yeah.
Yeah. Actually, I haven't checked resolution dependency of the western jet position between the 14 and the 3.5 kilometer simulation. So so we expect that more realistic representation at 3.5 kilometer simulation in terms of the gravity wave propagation. So yeah, yes.
Excellent. A couple of questions still on, and we've got time if people have more questions to add in as well. We've got a little time left. So a comment from Praveen Kumar, who says excellent presentation. I think we'd all agree. And a couple of questions from Praveen. So first of all, did you observe instabilities or model crashes of these 3.5 kilometer simulations, and what were your experiences of that? So how stable is the model?
Yeah. Actually, I actually faced the instability problem in computation. And one reason for this is the implementation of the Leonard term. So Leonard term uses the horizontal gradient of scalar values or wind velocity fields. So in NICAM, the horizontal gradient is evaluated on the terrain following coordinate. So yeah, in a higher horizontal resolution, the slope of the mountain is becoming steep. So the evaluation of the horizontal gradient is more and more difficult, or more and more generate contrast. So that is one of problems for the numerical stability. So when I faced the numerical instability, I temporarily shortened the time interval in very limited simulation, and then we used but anyway, we sometimes changed a bit, used the smaller time step to avoid numerical instability.
And can I ask, what time step were you aiming to use?
The time step in this simulation is 10 seconds. And
okay,
if time, wow. Yeah.
Okay. And yeah, can I also just ask, were you doing anything in particular around smoothing orography? Did you have any particular challenges with that?
Yeah, actually, yeah, I actually the topography is somewhat smoothed compared to the real orography. But yeah, but that is not so appropriate because of the for example, the mountains, very high mountain cannot be represented in our simulation, and so yeah, we need to modify it in order to make it possible to use more complicated topography.
And just the final one, follow up on from Praveen on model crashes, was, did you have any issues around gravity wave propagation at the model top?
Uh, the
Sorry, the final one just come in.
actually, yeah. Actually, this is not so serious problem because of we adopted a sponge layer near the model top. So I don't expect such model crashes related to rapid wave propagation to the model top. Yeah.
Perfect. Okay, last couple of questions. The second aspect from Praveen Kumar was, can you speak about the diurnal cycle over land and how it's improved or changed with resolution?
Okay. Yeah. This is yeah. Skipping this talk. Yeah. So actually, diurnal cycle over land is drastically improved at the 3.5 kilometer simulations. So, for example, can you see this slide? So yeah. So this figure shows the precipitation diurnal cycle around the Sumatra Island, and yeah, in these regions we can observe the offshore and inland propagation of precipitation diurnal cycle in a daily scale. And actually, yeah, K-scale can improve the onset timing of a round compared to the train observations. And we also can simulate it in the, we also succeed in simulating the inland propagation of a round appropriately. But we have also a problem in amplitude. The precipitation diurnal cycle over round tends to be underestimated compared to the observations. So yeah, the onset timing over round is very drastically improved, but amplitude has still some problem.
Thank you. And the final question from Richard Forbes on a related theme, saying that you showed the frequency of the small scale convective cells are overestimated in NICAM. Do you have a feeling for what that's sensitive to in the model and what your plans are for improving that?
Yes, thank you for the questions. Yeah, actually, I haven't checked it using a 3.5 kilometer simulation, but based on my experience of the 14 kilometer sensitivity simulations, the microphysics, the treatment of microphysics has a big impact on the spectral of convection, the spatial scales of the organized cloud systems. And we also recognize impact of the Leonard term on producing more wider cloud systems, but more wider cloud. Yeah, so the because of the moisture diffusions has an impact on being favorable for more organized systems, which contributes to a reduction of the smaller scale competitive systems. But this sensitivity is not so strong. But yeah, so such kind of model physics can certainly affect the representation of small scale convective cells. But all of those model improvements cannot resolve that issues necessarily.
Fantastic. And thank you again for addressing all of those questions. I appreciate it. It's a difficult task, particularly at in your time zone currently. So we very much appreciate the early start to your day, Daisuke, and for sharing those results with us and for such considerate responses to the questions. So thank you so much again. I suggest if anybody on the call now or those watching the recording back online have further comments or things they'd wish to explore, then please contact Daisuke directly, and I'm sure there's opportunities for further collaboration and interaction from here. So thank you again, Daisuke, and a wonderful talk.
Yeah, thank you for organizing this webinar. And thank you
A
for
pleasure.
yeah, very active discussions for participants.
Yeah, and if others have feedback on the event, then please feel free to get in touch with myself or with Rosie or Kelly as co-conveners, and our email addresses are up on the slide here. And a reminder, you can go onto the WCRP webpage and find the recording of this event will appear there alongside of the others. So please encourage your colleagues to catch up with the event in slower time as well. In terms of future events, so next time around in 2 months' time, on the 12th of March, we're looking forward to a presentation from Dr. Francois Engelbrecht from the University of Wits in South Africa, talking about a K-scale weather event attribution system developed in the Global South. For those who've registered for this event, you should get a notification nearer the time with another invite again to register for the Zoom participation. And we look forward to seeing you there. And with that, just one final thank you again to Daisuke and to all of you for joining today. And with that, we wish you a good rest of your day. And thank you all, and we'll see you next time. Take care all.